So let's see now how Java deals with key value stores. So we have looked at the collections interface. So the collections interface captures data structures like arrays, lists, sets, etc. So these are groups of values, but they are only single values, right? So in this single collection, there may or may not be a way of indexing them by position. For instance, arrays and lists will give us a positional index. So we will have a sequence of values. In a set, we have an unordered collection of values. Now the other important class of data structures is that called a key value pair. So this is what Python calls a dictionary, for instance. So here you supply not an index, but an arbitrary key, and against this key a value is stored. So the Java name for this interface is map. So map is disjoint from collection. It's a different interface. So things which come under collection are not under map. So map and collection are two incomparable points in that tree of Java interfaces. So with a map, we have two quantities, right? So we have a key and a value. So this is therefore a kind of generic interface parameterized by two types. So there is the key type and there is the value type, right? And typical things that you need to do obviously in a key value store or in a dictionary is to access a value and to insert or update a value. So these normally when we use Python, we use this square bracket I notation, which is common to both lists and dictionaries. Whereas in Java, you actually have to use these functions called get and put. So get will take a key and produce a value. So the return type is v, the value type of this thing. And put will take a key and a value and insert it, right? So we will come back a little bit to discuss why this has a return type v. But the other thing that you can do, of course, which you need to do often in a dictionary or in a key value store, is to check whether a particular key or a particular value is present. So Java provides these contains key and contains values functions as part of this interface, which allows you to provide a key or a value and check whether it's there or not. So the Boolean will obviously return true if the key is present and not true or false if the key is absent, and so on with the value, right? So before we go ahead and discuss why this put has a return type v, another thing which is worth noting here is the discrepancy between, say, this put. So put is the only one which actually seems to insist on inputs following the type that is associated with a generic map, right? So when you want to put a new pair k comma v into the map, you need to make sure that the value key that you supply is of type k, the value that you supply is of type v. On the other hand, when you get something, it is sufficient to provide an object. Similarly, when you search for something, I am asking, is there a key or is there a value present in my key value store? It is sufficient to provide an object. So now this is a kind of design decision of Java. This is one of these many things which, one can question and ask whether this is the correct way to do it. So you could argue that this should be a k and this should be a v and this should be a k, right? If I am going to get the value associated with a particular key, the key that I provide should be of the type that Java expects. Similarly, if I want to check whether a key is there, the key should be of the type that Java expects. Similarly, if I want to check a value, the value should be. So why do we have object? Well, in a sense, what are we asking? We are asking whether the key that we provide or the value that we provide is present. So what we are really asking is that internally, what Java needs to do is compare the existing keys and values with the key or value provided using the equals operation, right? And equals is defined usually to also take object. So in a sense, by providing this object as the type of the input, Java provides more flexibility. So for instance, you might have a data structure in which equals is more generous than syntactic equality. For instance, we said that for sets, two sets would be the same if they have the same values, but they are not necessarily in the same order. Earlier we looked at data structures like date, for instance, where we said that two dates would be the same if they actually contained the same month, day and year. So there might be different objects which represent the same value in some sense, which could be equated by equals. So by providing this possibility of providing an object as an argument, what Java is saying is that you provide me some representation of the key or some representation of the value that you're looking for. I will tell you whether there is an equal representation present in my key value store. Whereas if you want to actually insert something into the key value store, then you had better be sure that the values that you're inserting are of the proper types. Now, as I said, this is a kind of debatable point, whether this generality of allowing an object is a good thing or a bad thing. It's a good thing in one sense because you're not constraining the use of this get and contains key and contains value. But it's also a bad thing in the sense that now it becomes a type checking problem, because Java is not guaranteeing at compile time that the key or the value provided actually matches the type associated with the generic data structure that you're using. So then as the programmer using or implementing this, it's your job to actually check this. So you end up having to do some extra sanity checking of the types. So it is a design decision. Partly this design decision is due to this issue of legacy, right? So remember that generics were added later. So many things in generics are actually designed to work with objects, because earlier that was the only way to write this kind of generic code. So there are various things going on behind the scenes, but it's important to note this, this discrepancy in this interface, that only the put actually uses the types capital K and capital V, and the get contains key and contains value all allow a generic object to be passed. Okay, so now let's get to this issue, right? So why does put return something of type V? So we all know that in a dictionary, you cannot have two entries for the same key. So the keys form, from an abstract point of view, a set. There can only be one copy of each key. You cannot have two different keys which are equal to each other. So if I now update the value at a key, the old value gets overwritten, right? So this is what happens. Either I create a value, we will come to that, or I overwrite the value that is there. So when I overwrite, the old value in some sense is not available anymore. So what Java says is that, okay, since you are offering this through a put function, it offers you as a bonus to return to you the current value, right? So put kv updates the value associated with the k. So it is like in a dictionary you would say dk is equal to v. That's what the put kv does for you. But in addition, it gives you back the old v prime. So there was already a value v prime associated with this key. So what put does is, it when you update it to a new value, it gives you back the old value, and that's why the return type of put is actually v and not something like boolean, did it work or not, or void or something like that. One of the typical uses of a key value store is to accumulate quantities. For instance, if we are running through some text and we want to count how often each word occurs, we use the words as keys, and against each key, against each word, we maintain a count. So every time we see that word again, we increment the count. Similarly, we might accumulate, for instance, the runs scored by players in a tournament. So we might use the name of the player as a key, and for every score that is added to that player's record during the tournament, we will update the sum. So we will keep adding scores, and at the end, that key corresponding to the player's name will record the total runs scored by that player in the tournament. So whenever we do this kind of accumulation, there is always an initialization problem. That is, the first time we want to do something differently the first time and the next time. So the first time we encounter a word, or the first time we encounter a player's runs, we need to create an entry, right? So we need to initialize that particular entry by creating a key for that word or that player, and setting the value to be, in the case of the word, if it's a count, we will set it to 1. If it's the case of the player's scores, we will set it to the initial score. Subsequently, if the key is already there, then we don't want to overwrite it, right? What we want to do is update it. So if it is the count, we will increment it. If it is the score, we will add the new score to the old score. So whenever we work with these key value stores or dictionaries, we need to have a mechanism to do this. So one mechanism that Java provides, which can be used for this, is a default method. So this method actually is given to you in the interface by default, right? So it is provided to you, whether you write it or not, you get it. So what this get or default method does is, it takes a key and it takes a default value as an extra parameter. So the way you use it is like this. So for instance, supposing I have a map, right, a dictionary, in which the keys are of type string and the values are of type integer. So this may be the scores of a player in a tournament. So the string is the name of the player, and the integer that is associated with that is the total runs scored by that player so far. So now if I pass a particular player's name, so a particular batsman's name in bat, Now, if there is no key, then this will give me an error, right? If there is no key called bat, this will give me an error. So what get or default does is it says, okay, I provide an extra argument 0 along with the call. So if there is an actual value for this key bat in the dictionary or in this key value store, I will get that actual value. If there is no value there, then I will get 0. So 0 becomes a default return value to be returned back in case the key is not present, right? So this is an extra version of get which Java provides, get or default. So you can provide a default value. If the key is there, you get the actual value. If the key is not there, you get the default value. So how do we use this, right? So now what we can say is that if I want to update a value, so I get a new score, right? So I want to update a value, so I want to take the existing score and add the new score and put it back for the batter. So there is a batter called bat. Against this batter's entry in the dictionary or in the key value store, there is already some total runs accumulated. I am adding one more score to that. So I want to take the existing value. So I want to take the, so if I normally do it, I would just take get the current value of the score bat and add new score and put it back, right? So this is a two-step process. I get the current value, add new score to it, put it back. But now because I'm not sure whether that person actually has an entry, I use this get or default. So what this get or default will say is that, okay, I initially get either the current score or I get 0, which is a valid starting point for a new entry, and then I want to initialize it. I mean, essentially in this case, initializing it to the new score I just got, which is the same as adding 0 to that and saying put back 0 plus the new score. Right? So this is an indirect way of doing this in one shot without having to explicitly check. Of course, you can check, as we will see, you can check. The usual style would be if the key is there, then do this, else do something else. But without actually having to check the key, you can use this mechanism of get or default to do this two-type update, right? Either create a key or update the value. Now, this is not the only way to do it. So there is also a method which Java provides called put if absent. So as the word suggests, this creates a new entry if there is no existing value for the key. So for instance, if I want to initialize the batsman's key to 0, provided there is no, I don't want to override an existing thing, but only if there is no key for this batsman, I want to create an entry with 0. I can say put if absent bat comma 0. So what this will say is if the key bat exists, do nothing. If the key bat does not exist, create a new key value pair with the key bat and the value 0. And now once I've done this, I'm guaranteed that there is either the newly initialized 0 or there was an existing value. So this get or default that I use there can be simplified to just a get, right? So now I can safely look up the key bat, get the value by get, add new score and put it back into bat because of the put if absent, I've guaranteed that that thing actually exists. So this is a different way of achieving the same thing as this get or default. And Java actually provides a third flexible way to do this, something called merge. So what merge does is it takes the name of the map, right, and applies a merge to it. So you provide a key, right, you provide a new value, right, and you provide a merge function. How to combine the new value with the existing thing. So merge builds in this kind of initialization. So if there is no existing key, then it works like this part. Right, it works like this put if absent kind of thing. It creates a key for bat and inserts new score into it. If there is a key already, then it takes the two values scores get bat, scores.get bat and new score and combines them using this function. So here the function that we have provided is the sum function from the integer class. So this is a kind of static function in the integer class. So it says take the current value of the score associated with bat, take the new score which I am providing you now, combine them using bat. So this is combine them using sum. So this is a third and flexible way. It says either initialize to the new value or take the old value that already is there, the new value, and combine them using the function I give you. So Java has many ways of doing this, so you have to choose the way that you are most comfortable with. But as we will see, you can also do an explicit thing. You can also check if it is the key is there or not. So how do you check if the key is there or not? Well, we need a way of extracting, as usual, from a key value store, the collections of keys, values, and so on. So remember in Python, you would use something like d.keys or d.values, right? So these are two built-in functions which for any dictionary D will give you the list, not quite a list, but will give you a kind of sequence of keys and values that you can run through a for loop. So similarly, the map interface provides these three functions. So there is key set, which will return the keys, values, which will return the values, and entry set, which will return pairs. It will return the keys and the values together. And now these have different types and also different characteristics. So remember that keys form a set. Right? There is only one entry per key. So therefore, the return value of key set is a set, and it's a generic set of type K, where K is the key type of the corresponding map. Right? So if I have a map with key type K and value type V, the key set function will return back a set of type K. Right? So set in the sense of set in the collection interface. So it will have all the functionality associated with the set that we already saw in the collection interface. On the other hand, values have no particular structure, because I could have, of course, many different keys having the same value. Like think of frequencies of words. Many different words could appear with the same frequency, or many different batsmen could have the same number of runs. So values is just a collection, right? And it's a collection again of type V, because that is the type that we associated with the values in our key value store. And now the last thing is I actually get back pairs, right? So these pairs are of the form K comma V, but they are not pairs in the usual sense that we use in Python. They are not just a set of pairs like this, right? They are actually from a type called map.entry. So the key value pairs, now again, remember that the key is unique. So with each key you could have only one value. So if I look at the pairs key comma value, they must also be unique. I cannot have two different key value pairs which are the same, because that would imply that they both have the same key, which is not possible. So again, this is a set, and the type of value stored in the set is this complex value, which is a map entry of type K comma V. Right? So these are the three functions that Python, that Java gives us to actually take a map object and produce something from the collection object. So Java calls these views. So we are used to this from a language like Python, saying that I can extract from a dictionary the sequence of keys and the sequence of values. But here now remember, in Java you have on one side collections, you have one side maps. So what this is providing is a way of translating some kind of a slice of the map in the form of a collection, either as a set of keys or as a collection of values or a set of key value pairs. So as you would expect, you can now take this representation and run through your dictionary or your key value store systematically. So for instance, if you want to go through all the entries in a key map called a map of whose keys are strings, right? So let's call it str map. Then you first extract the key set from it, and now you will use our familiar for loop to go through this set of keys, right? So keys now is a set. So we can go through it using the for loop, or we can actually, if you want, explicitly create an iterator and use the iterator. But remember, this for each loop is a kind of simplified version of the iterator. So for each key in this set keys, we can do something with it. So this is a simple way to do a kind of batch processing of an entire key value store. So typically when we do this, we will take the key and we will go back and ask for the value associated with the key. Right? So there is a two-step process happening here. We are getting the set of keys, and for each key we might again query the value. So that's why this entry set is provided, that you don't have to go back to the map and query it. You are given the key and the value together. Right? So for instance, if you take entry set, you can again run the for loop, but now the for loop will be this mysterious thing. So it will be something of type map entry with the key type and the value type. So this variable entry which runs through the key value pairs will have this type. And I need to extract from it the two parts, right? So the projection, the normal pair, you want the zeroth component and the first component. So it's obtained in this case by get key and get value. So I take this entry, it's a complex object. It has the key and the value, and we're cycling through every key and every value present in our map, right? And now for each of those individual complex things, I can extract out the string part and the employee part, because this was a map in which the keys are strings and the values are employees. So then I can do something with the particular key and the particular value that I get, right, and proceed. So once I am able to extract keys, values, key value pairs as collections or sets from my map, then I can use all the iterator functions of collections in order to run through it. And in particular, going back to our previous question about, checking whether something is there and then adding to it. Well, here you can imagine, see, the thing is that if you want to check it, it's not as easy as saying in Python if k in d dot keys, right? You cannot just do this as you would in Python. Instead, what you have to do is you have to first extract the key set and then check whether it is in that. So every time when you update the keys, obviously the keys change. So each time you update the keys, you have to recreate the key set and so on, which is why it's useful to use those other methods that we talked about, like get or default or put if absent and so on. So this is all, remember, at the level of the interface. So these are all things that are promised to us by the map interface. So the map interface comes with these get put functions, the contains functions tells us whether a key or value is present. It gives us these get or default and put if absent methods. So all of these things are available to us because they are part of the map interface, and then you have concrete implementations of these, just as we had collections. So the first concrete implementation is in the form of a hash table. So there's something called a hash map. So remember, a hash table basically allocates something like an array, and in a hash set we took a v and we mapped it to some position h of v, and then we put the v here. So this is what a hash table was. And now if we had a v prime which came to the same thing, then we had to do something about this collision thing. Either we move it down or we keep some auxiliary storage or something. So there is some kind of way of handling these collisions. So like a hash set, a hash map will do this, but now remember that because I have this possibility of collisions, I cannot say that, I cannot take a key and get back the value that produced it. I mean, I cannot take a position in this table and identify the key value. So what I will have to do now is store not just the key in each entry, but I will have to store not just the value, but the key and the value. So that's the only logical difference between a hash map and a hash set. In a hash set, the value itself is used as the input to the hash function, and what is stored is at that position is the value, right? And the position is determined by v. Now here the key is used to determine the position, and you store at that position both the key and the value, because you cannot interpret that value, the position, to recover the key. So like in a hash set, because we are kind of putting these things into the position based on the outcome of the hash function, there is no fixed order. So this is an unordered hash map. So if I take out, for instance, the set of keys that comes with this, it will be processed by an iterator in some order, but we cannot predict the order. So if we want an order, then just like we had tree set, if you remember, we had tree set, which was a concrete implementation of set, which underlying it use a balanced search tree. Similarly here we can have a balanced search tree underlying a map called a tree map. And in this case, the keys actually are always available in sorted order. So if I take out a key set from such a map, then it will behave exactly like a tree set. It will give me the keys in sorted order if I run an iterator to it. So tree map corresponds to tree set, hash map corresponds to hash set. There is another thing which is available in both, but we will first see it in the context of hash maps. So there is something called a linked hash map. So here I have typically, remember, a hash table, right? So in this hash table, I have different entries. I have k1, v1, then I might have k2, v2, and so on. And these entries could have been added in any order. The positions are determined by the hash function. Now what a linked hash map does is it kind of remembers. It says, supposing k2, v2 came first, and then k1, v1, then it will separately maintain a link from here to here. And then k3, v3 came next, it will maintain a link. So superimposed on top of the hash table, we have a linked list structure. And in fact, this linked list structure is actually a doubly linked list. So we also have backward pointers, right? So we can traverse this linked list from beginning to end, or so we can talk about, so we can find the most recently inserted value in our hash map, we can find the least recently inserted value in our hash map, right? So this doubly linked list. So what this means is now I can, so this is, remember, this is a hash map. So there is no other order assumed. It's not a tree map. But in this hash map, I am just remembering the order in which things were inserted. And by doing this, I can then process these elements in that order, either in the order in which they were inserted or in the reverse order, because it's a doubly linked list. I can go backwards also. So I can go from end to beginning or beginning to end. So I can now process things in the order in which they were inserted. And if you think about the Python dictionary, so actually in a Python dictionary, when I say d.keys, the older versions of Python did not promise you anything about the order, but the current versions of Python after 3.6 or something promise you that d.keys actually returns the keys in the same sequence in which you put the keys in. So really a Python dictionary is implemented using something like a linked hash map. It has a hashing part which kind of uses a hash table, but it also maintains this kind of linked structure to let you go backwards and forwards between the keys in the order in which they were inserted. So Java goes one step further. You can also change this linked hash map not to process in terms of the order in which the keys were inserted into the hash map, but in the order in which they have been used. So there could be a value which was inserted a long time ago which has not been used, but another value which was inserted just after that has been checked again recently, or it has been updated. So either a get or a put against a key indicates a usage of that key. So that key has been used recently, and it could have been a very old key, it could have been put into the map a long time ago. So the order of insertion into the map is different from the order of access. So we can, I will not tell you the exact syntax, but we can actually set up a linked hash map in which we tell it that the order you should remember is the access order. So what this really means is that whenever I get or put a key, the links are changed so that that value goes to one end of the list. Remember that the list normally goes from the earliest to the latest. Now it will go from the least recently used to the most recently used. And this is important because there are many applications where we really want to know which values are recently used. So typical examples are scheduling and caching. Right? So when we are scheduling, if we are maintaining a list of things that need to be done, and each of them is being allocated some amount of time, then one of the strategies which is often used is to choose for the next slice of time the process or job which has been least recently scheduled. So if you can maintain some kind of fairness across these. Another situation is caching. So caching refers to the idea that if you're running out of memory, you can put some of your, so the data from your memory can go onto the disk, or you might have, in certain cases, you might have some super fast memory inside the processor, and you might want to keep a subset of things there. So which are the things that you need to keep in fast memory and which are the things can go to slow memory? So typically when you run out of space and you want to bring something in from the slow memory to the fast memory, something has to go out. And usually there what goes out is something which you have not used for a long time. So imagine that you have a large collection of books in your house. So you have a bookshelf in your bedroom which can store all the books, and in your living room you have a small bookshelf where you can keep 10 books. Right? So these 10 books, now at some point you want to read a book from the bedroom and you want to keep it outside. So one of these 10 books has to go back to make space for it. So which book will you put back? The one that you have not read for a long time. So that is this least recently used policy, and that can be implemented using this access order in a linked hash map. So just like there is a linked hash map, so just like hash map is like a hash set and tree map is like a tree set, there is also a corresponding linked hash set. So even in a set, we can have the elements in the hash table linked either in the order in which they were inserted or in the order in which they have been accessed. So it doesn't have to be only for a key value store. Even for a set, we can use the same data structure. So to summarize, we have two separate interfaces in Java. Right? We have the collection interface which talks about things which are not key value stores, and we have the map interface which captures the properties of key value stores. So the key value store requires us to associate a key with a value. So get will tell us the current value associated with the key, put will insert a new entry for a key, and contains key and contains value will tell us whether a given key is present or not and a given value is present or not. So here it's a generic data structure, it's a generic interface which has two parameters in terms of types, one for the type of keys and one for the type of values, because they can be from different universes. I can have a different type of key and a different type of value, but like in every key value store, like in a dictionary, think whenever you see key value store, think of a Python dictionary. You can only have one copy per key. So the keys will form a set. Then one of the fundamental problems that arises when we update values in a key value store is to decide whether or not it's the first time we are assigning it or whether we are updating it. So we have these different mechanisms which allow us, without explicitly querying whether a key is present or not, right? We have different mechanisms to actually get hold of these values and update them, right? So we have this get or default, put if absent, and merge. And then, as in any reasonable key value store, we can extract out the collection of keys and values, and in this particular case even the key value pairs, using this key set, values, and entry set. So remember, values will give you an arbitrary collection. The other two things will give you specifically a set, because there can only be one key, one copy of every key, and there can only be one copy of every key value pair. So these are called views, and using these views we can run this for each loop or run an iterator to run over a data structure. And then we saw that there are three very concrete implementations which are commonly available in Java for this key value store. There is a hash map, which is like a hash set, a tree map, which is like a tree set. So a hash map uses a hash table, a tree map uses a binary kind of a search tree in order to maintain it. And a linked hash map is a augmented hash map in which we additionally maintain a linked list structure between the entries in the hash table, so that we can keep track of the order in which they were inserted, or we can keep track of the order in which they were updated. So we can talk about the most recently used and the least recently used.